Thank you. Do you hear me? Yeah, I can see it. It's very scary. Timer. Okay. Thank you. I'm not Paulina, but I will give the talk for her because she couldn't make it. So this is going to be the talk about her work on the single long slit spectrometer of MICADO. So as you know, MICADO is will be a unique instrument that will be able to do a characterization of the atmosphere of the exoplanet in the near infrared with high resolution spectrometry in the first years of the ELT before Andes and Harmony comes online a few years later. So that's mostly the talk of Paulina was about that. Now I want to talk a little bit about high contrast modes and do an advertisement of my poster right after that. Just to let you know that MICADO also has high contrast mode, and one of the first one is the good classical Leo coronagraph, just the one that was invented a few years ago for the sun. And we have like 3 Leo coronagraphs with different diameter that allows optimized for different atmospheric conditions, distance to the zenith, and also wavelengths. And this coronagraph can be used with different filters, obviously, in JHK, and they are coupled with a Leo stop. So this focal plane have a Leo stop, as in the real former Leo coronagraph. So that's really in the spirit of Leo. And it could be combined also with the natural density filter to allow the calibration of off-axis stars to do photometry. There's also a vector apodized pupil coronagraph that allows us to reach closer in to the star, down to 2.6 lambda over D. And then another element which are 2 sparse aperture masks that allows to go even closer to down to below lambda over D with the moderate contrast. So that was important, I think, to show that for the spirit of Leo. And I will just advertise my poster, which is number 5, just showing like nice pictures only. It just gives you an idea on these images simulated of MICADO, how we will be able with MICADO to dive into the core of the system, the exoplanet system we have. We will be going much closer than a sphere or even Miri, obviously. And well, in these images, I added some planet that you can expect to find around your favorite star here at HR 8799, or eventually some inner disk that might be there. Okay, this is just fantasy, but it just gives you an idea of how good we will go much closer in. Now, back to the, and then, yeah, another point is also the sensitivity of the instrument would be much better. And this is an example on the TW07. This is the red part here are the sensitivity of MICADO, which is way much better than Sphere, which is up there, the blue one. So we will be able to really go also for very faint and low and light objects with MICADO. So come to see and talk about that and other things around my poster if you want. So back to the long slit spectroscopy. So there is two slit. The one we will use for exoplanet would be the one that is 3 arcsecond length and has a 15 mass width. It can be used in different mode, and we will focus on the H+K mode at 20,000 resolution spectroscopy. One thing that is important to note is that there is no ADC in front of the slit in this in MICADO. So that means that we will have to align the atmospheric dispersion with the length of the slit. It also means that we will have to work with pupil tracking mode. It also reminds you one thing. We are an ALTAS telescope. That means that the planet, the position of the planet will move with respect to the diffraction of the telescope, which may be a big issue, as we'll see later. So let's do some simulation. Paulina, for the simulation, took a planet that we know, we heard about it several times already this week, so AF-LAB-B, and we took it in June 2030. At that time, it will be around 200 mass from the star, and we know that the contrast is about 10 magnitude in K. So with this element, we can simulate, we have the planet, now we need to simulate the star. So to simulate the star, we have to take into account the variation due to the residuals of the EOS system. And this is what you have here. The frames here are separated by 1 second, and the exposure time, obviously, for the spectroscopy would be longer, so we can average over 30 seconds, but we could see that there's averaging, the images are slightly different. So there will be variation of the speckles. We don't see it very well here, I saw people moving around. Yes, there are some variation, and there is the variation with time of the speckles, obviously. But more than that, there will also be variation of the speckles with respect to wavelengths. And that's well pointed here, where we have like 3 wavelengths, 3 images of the PSF at 3 wavelengths. If the planet is at the position 3, for example, you can imagine that since the diffraction pattern will increase as a function of wavelengths, well, there will be a wiggle in the spectrum. That's what we see here, the position 3, as a function of wavelengths. The intensity is varying just due to the star itself. So when you have the planet here, you will have some issues, obviously. So you'd better go in the position 4, obviously, but even at 4, there's still some wiggle. So now we have like the star. Let's compare them. So what will happen is that as we are fixing the pupil tracking, there will be some rotation of the planet around the star due to parallactic angle rotation. This parallactic angle rotation will depend on the distance to the zenith. Now we don't want to do some multiple simulation to track that, but here what Paulina did is taking something that's unrealistic, but has a uniform rotation of 60 degrees from 30 to 90 degrees here over 30 minutes. It gives you an idea to estimate the effect of the diffraction from the PSF itself. Remember, there is no coronagraph here, on the estimation of the planet. So the planet is in the middle of the slit. The slit is here very small. In fact, it's much larger than that, but just for simulation purposes and size on the computer, we don't need to have like a 3 arc-second simulation here. And it's just here in the middle, and we are measuring the intensity for the planet and for the star. And this is what is written here. There is length of the slit as a function of the angles. For a given wavelength, it's 1.5 micron. For the star here and the planet, you can see the planet is almost always at the center. There is small jitter due to the jitter of the PSF of the planet itself. But for the star, there are lots of speckles here that you can see. Now we have these elements, and we can gather them in a formula that will give us the intensity that we will measure at the end on the detector, and eventually after post-processing getting us the spectrum. So what we will do is multiply this information that we have on the slits multiply by their and yes, and as I said before, the planet will be rather flat here, while the stellar residuals will be wiggling, as we saw before. Now we will multiply these things by the spectrum of the planet and the star, apply the right contrast that is measured on AF-LAB-B, and we have like this kind of models, and then we will add some noise, and we can also multiply by a transmission that will take into account the telluric, the detector effects. Here we're not taking into account, but that can be done here. So if we do that, then this is what we get. This is the length of the width as a function of wavelengths. So you have a hit here also in wavelengths as a function of for all the angles that were scanned. So the first thing we could see is that we can very easily see the spectrum of AF-LAB-B. So for MICADO, it will be a very easy target. Now, there are some positions here and here, as we saw before, around the diffraction of the spider that we want to avoid. So that's going to be an operation issue. So we will have to define when we want to observe this object during the night. We can probably go to much fainter planet, indeed. And now we can still remove, because there are still some residuals. So we can remove some of these elements by using a cross-correlation technique. And this is what we get. Here we see that we are really recovering very well the planets. It's quite logical because the spectrum of the planet and the star are rather very different. But there is still some issue, as I said before, at the angles where the spiders are. Paulina also tested by shifting the cross-correlation by a few amounts in wavelengths to see what kind of radial velocity we can measure with MICADO. And she found like something around 18 kilometers per second, which is very close to what we are expecting from a 20,000 spectroscopy system. Now, this is all the work that has been done so far is ready for doing this a complete parameter space exploration. So you going from contrast, separation, planetary parameters, atmospheric parameters, sorry, planetary dynamic parameters also, and this is going to be the work that Paulina is starting right now. I will let you on the closing remarks and ask for questions.
Hi, given the constraints on the positioning of the slit, are you worried about saturation for the star? Like, do you know what kind of magnitude you're going to saturate at? And is that going to be limiting possible planets you can characterize close in?
Well, I mean, the star will never be in the slit in general, mostly, except, yeah, if you are really at the top. And we haven't looked at that yet, yeah. Now, we can always put the slit a little larger, so moving the star further down eventually. But that's one point that has to be taken into account. We are 20,000 resolution, so, but we are an ELT. We have an ELT, yeah. Yep.
Okay, I have a question about the slit positioning, because the slit is roughly lambda over d, I guess, or like the width?
Slightly more, yeah.
Slightly more?
15 mass. So
15. So you need to have a very accurate knowledge of the position of the planet. So do we need to do follow-up campaigns of a lot of these companions to constrain the orbit? Because we might not know where they are, like 5 or 10 years in the future.
So there is a complete, yeah. So for the planet, we will see it's going to be easy because we will know, we can measure them beforehand. Now, if we don't know them and they are really faint and we need to do the post-processing to get that, that's going to be more complicated. Yeah. So we will probably need more information on their positioning and orbiting period. Yeah. So gravity will help a lot on that. Since there is, I just wanted to advertise that. So we have like, in our team, we have more than 7 positions in the next 2 years, thanks to a grant that was afforded to Joanne Mazoyer. So just if you are interested by postdoc and PhD on all these subjects, SCC, CDI, observation on sphere plus, preparation of sphere plus, MKIDS, come and talk to us or Mamadou for some of them.